Great, thank you. So I'm talking about, our results from our paper, Shorter Quantum Circuits, and this is work done with Vadym, Vadym, Christophe, and Kristin, and myself. So this is the situation we're interested in. We have a researcher who wants to solve a very difficult problem on her very realistic fault-tolerant quantum computer here. She's lucky enough to even have an algorithm for solving this problem. However, it may be the case that the implementable operations or gates that are available to her computer don't match those required by the algorithm. And so she has to go through some process of translating this algorithm into a circuit that she can run. And this process is known as quantum compilation. However, it often incurs a cost of increased runtime, increased gate count, in other words, a longer quantum circuit. Moreover, she's working with a restricted set of gates here, so this final circuit is likely to be an approximation of the original, but she'll set some allowable threshold of error epsilon. When you factor in other processes like state distillation and error correction, which increase the cost, we end up in a situation where, although our researcher now has an implementable circuit, it's now too expensive for her to run. And that's where we come in. So the purpose of our work was to reduce the cost of this compilation process by looking at the cost of gate approximation, by which I mean the problem of finding a sequence of gates from your implementable set, the product of which is epsilon close to some target. And as the name suggests, our results do in fact lead to shorter quantum circuits and a very happy researcher. And these sort of reduction in compilation cost results are applicable to kind of more general resource estimation problems. If you're around on Wednesday in the industry session, you would have heard the results from Microsoft, and they use a number of our results in their implementation. So the upshot is we end up with happy researchers all down the quantum stack. So the standard approach to these sorts of approximation problems is to reduce as much as possible to the simplest case, that is a single qubit Z rotation, which of course has a diagonal unitary representation, and we know how to approximate these. So for Clifford plus T, for example, the cost of a single diagonal approximation is 3 log to 1 over epsilon, due to Ross and Selinger, as Greg mentioned. So in our work, we introduce a cheaper method known as the magnitude approximation, which only costs 1 log 1 over epsilon. And so you can reduce the number of diagonals you're doing, and we get circuits that are a little over 2/3 of the cost of the circuits coming out of the all-diagonal approach. So that's great. We're already getting shorter quantum circuits, but we also additionally look at reducing the cost of these diagonal approximations as well. So let's suppose your target is a diagonal. So here's our Z rotation. There are 3 known methods for doing this sort of approximation. The first of which is just a standard diagonal approximation. This is the work that Greg touched on. There are a number of algorithms that are kind of optimized for specific gate sets, and the recent work all follows this highly number theoretic approach that was kind of pioneered by Kliuchnikov, Maslov, and Mosca. Then there's fallback approximation, which is a protocol proposed by Bokharov, Rotler, and Svor, and it kind of uses this idea of taking measurements and using feedback to get a cheaper approximation. And thirdly, Earl Campbell and Matthew Hastings independently realized that if you're able to take a probabilistic mixture of diagonal approximations, you'll actually also see a reduced cost of approximation overall. And I think if you were here at, or not here, but at QIP a couple of years ago, Earl actually presented on this algorithm. So both fallback and this mixed diagonal approach employ diagonal approximation algorithms as kind of black boxes. So it was huge motivation in our work to open up those black boxes and kind of unify the standard number theoretic approach across all approximation instances. In doing so, we also ended up introducing a 4th method of approximation which combines fallback and mixing. And you can see the benefit of doing this numerically. So this is a chart showing approximation cost in terms of T count, the number of T gates, as a function of accuracy, or epsilon. And this is for Clifford plus T approximations of random Z rotations. We're of course looking for a cheaper cost. So the flatter line the better our approximation method. And so the blue line here is the standard diagonal method, and then the other three are implementations of our kind of unified approach to mixed diagonal fallback, and then at the bottom, our new mixed fallback method, which is, in fact, the cheapest approximation approach. So this is the kind of the four-step procedure that describes the standard diagonal approach, which will which we will apply to all of these other approximation instances. But before I go into those details, I'll just briefly cover how it works for the standard case. So this is our target rotation in blue, and we want to find some unitary V that is epsilon close. And we're using the Clifford plus T gate set here, so we know that V is going to be of this form, but we don't know the power n in the denominator here a priori. So we proceed as follows. The first step is to find an approximation region, and we do this by taking the epsilon constraint on the difference between the approximation and the target, and we find that that actually reduces to a constraint on only the top left element of V. So this lowercase u in blue here. And we can represent that constraint geometrically by the region outlined in red. So any point from that region corresponds to a potential candidate for lowercase u. So the second step is then to enumerate the points from that region. And in order to make use of kind of efficient integer point enumeration algorithms, we can scale this region by increasing powers of the normalization denominator here. So then for each point that you enumerate, you have to solve a corresponding norm equation in order to ensure that V actually does lie in our gate set. And the power n in the norm equation will be exactly the same power n to which you've scaled your region. So lastly, once we've constructed our approximating unitary V, we synthesize it exactly over the Clifford plus T basis gates. So all of GI are either Clifford gates or T gates. And the interesting thing here is that the power n that we see in our norm equation and that we've scaled with ends up giving us the number of T gates in our final sequence. So n is actually our measure of the cost of this approximation. Okay, so returning to the unified approach, we made a number of kind of adjustments and improvements, and I'm only going to talk about two today, which both kind of affect this first step of finding the approximation region. So first, I'll look at the magnitude approximation, and then I'll talk about the extensions of this probabilistic mixing idea. Okay, so to introduce magnitude approximation, let's take as our target just an arbitrary single qubit unitary. So U here is just an arbitrary unitary in SU2, and this is the corresponding Euler angle decomposition. So as I said, the standard approach would be to turn everything into a diagonal rotation and then do three diagonal approximations for a total cost of 9 log to 1 over epsilon. And at this point, we can make a very simple but very important observation. Namely, the cost of the diagonal unitary approximation is relatively angle agnostic. That is, this leading order term only depends on our choice of epsilon. So let's reset and see how that can help us find a cheaper approximation. So this time, we're going to attempt to approximate the central X rotation directly. That is, we're looking for a V represented by this product in yellow, which is epsilon close to that central X rotation. And this is where our observation comes into play. So because the cost of doing the two surrounding Z rotations doesn't depend on the angle, we can take this psi1 and psi2 rotations occurring in the approximation and kind of absorb them into the surrounding Z rotations. So essentially, we're able to correct for parts of our approximation at no extra cost. So the psi1 and the psi2 rotations are introducing more degrees of freedom into our choice of central approximation. And that leads to a greater region of potential solutions, or in other words, we have a higher likelihood of finding a cheaper approximation. So what does this mean mathematically? Well, that epsilon condition is now only on the central X rotation of our approximation, and it reduces to a condition not on the top left element of V, but on the magnitude of the top left element of V, which is of course why we call it a magnitude approximation. Geometrically, this is now represented by a one-dimensional approximation region, the interval on the x-axis there. And the upshot is that the total cost of approximating our single-qubit unitary U has gone from 9 to 7 log 1 over epsilon. So before I move on, this idea as well is not limited to circuits involving Euler angle decompositions. It's any circuit where you have kind of Z rotations around that can absorb part of your approximation. So with that intuition in mind, I can hopefully justify the reduction in cost a little bit further. So once you've found your approximation region, recall that the second step of the algorithm is to scale that region with some power n, and then enumerate the integer points. So the obvious question to ask ourselves is to what power n do I need to scale before I first start seeing those integer points appearing? And we can employ a Gaussian heuristic here, which essentially says that if you have a subset of R2D and the volume of that subset is equal to 1, you can assume the existence of an integer point. And so that allows us to establish this relationship between the scaling power n and the area of our approximation region, or length in the one-dimensional case. Recall it also that n was giving us our t count, the number of t gates, or in other words, the cost of our approximation. So you can see, since the diagonal approximation region scales with epsilon cubed, that's why we get the coefficient 3 in our cost function. The magnitude interval length scales with epsilon, which is why we get the coefficient 1 in our cost function. So that's why magnitude approximations are cheaper. Now I'll talk a little bit about how we can also reduce the cost of these diagonal approximations, starting with this probabilistic mixing idea introduced by Campbell and Hastings separately. So the basic idea is that if you have multiple approximating sequences and you apply one according to a well-chosen probability distribution, then you actually get a quadratic improvement in epsilon when you look at the approximation channel and the target channel. So essentially, you've got your target rotation in blue here. You can find an over and under rotation, which may or may not be in your gate set. But then you can apply a standard diagonal approximation algorithm to find under and over rotated approximations, which by the triangle inequality end up being 2 epsilon approximations of your target. I'm hiding the details here, but you make a clever choice of P and you get an improvement in epsilon. So in our work, we want to open up these black boxes. And to do that, we use the following insight. If you apply a ZS twirl to each of the approximation unitaries, so to the over and under rotated approximation unitaries before then taking a probabilistic mixture, it simplifies the error between the approximation channel and the target channel, and it in fact simplifies it to a Pauli channel. And so then we can use a result from Magasan, Gambetta, and Emerson, which gives us a tight closed form expression for our approximation error. This allows us to define an approximation region which encompasses more solutions, and we get a corresponding reduction in cost. And it's by a factor half, you can see in the top right-hand corner there, which is what we expect from Campbell and Hastings' work as well. The region is given here in blue, and you can see it's very similar to the non-mixed case. It is larger, and it's also split between the over and under approximations. So the other method I mentioned is using fallback approximation. This is the unmixed case, so the original case, proposed by Bacharov, Rutler, and Svor. In this circuit, there are two main steps. In the projective rotation step, they attempt to apply a cheap rotation with some success probability Q1. And then if that fails, they fall back to doing standard diagonal approximation. So if we use our method to find an approximation region, we can see that it depends on the success probability, but it is in general larger than the diagonal approximation region. And that's why you see a corresponding reduction in cost to 1 log 1 over epsilon. So now let's also apply the idea of mixing here. Suppose we have two fallback circuits with success probabilities Q1 and Q2. In this case, we're mixing the channels associated to the whole circuit, so including both projective, rotation, and fallback steps. And that mixture leads to a factor half improvement in cost again. And just to remember, we saw that fallback and mixing was the cheapest method in our numerics, and that's kind of also proven by our heuristic justification of cost. The region, the associated approximation region, again, looks very similar to the non-mixed case, but is split across the two approximations. So it's probably easiest to compare them all when you see them next to each other. So the thing to recall here is that if you have a large area, you have more candidates for that top left element U, which means you have a greater likelihood of finding a cheaper approximation because you probably don't have to scale as far before you first start seeing integer points. And certainly, if you look across a row between diagonal and fallback, you can see that increase in area after some threshold value for Q. And then looking down a column from unmixed to mixed, this quadratic improvement in epsilon is captured in the change from delta to delta tilde. It's a little less obvious in the magnitude case, but you'll have to trust me on that one. So the results I've been talking about have all pertained to the Clifford plus T gate set, but we actually also looked at Clifford plus root T. And we found that, in general, you'll find shorter sequences using Clifford plus root T. However, the fault-tolerant procedures involved with Clifford plus root T kind of incur a T-state cost, so you end up with this space-time trade-off, and it's by roughly a factor of 2.5. And we saw this numerically as well. So these are two charts of approximation cost as a function of accuracy. On the left, we're measuring cost by non-Clifford gate count. So this is our sequence length or our time dimension. And on the right, we have approximation cost in terms of T count. And so this is our space dimension. And this is again for the same random Z rotations. And so we can see for the same value of approximation accuracy, we're ending up with that kind of factor 2.5 space-time trade-off there. But actually, our results are even more general than this. They apply to a wider family of gate sets known as quaternion gate sets. And I'm not going to go into the number theory, but essentially there'll be a map between your gate set and a quaternion algebra, and then you can take advantage of the number theoretic properties therein. So to summarize, the previous best known method was Campbell and Hastings mixed diagonal work, which we match. And then we also have two methods which get you cheaper approximations. And this space-time trade-off from Clifford plus root T applies across all protocols as well. I also mentioned that our work has been used for more general resource estimation problems. The second point here in particular, that's the paper that Microsoft was talking about, and our results are actually also implemented in the Azure Quantum Resource Tool. So apparently I've been speaking very quickly because I'm at the end. These links are all kind of related to our paper. I highly recommend the blog post, which is written by my co-author Vadym, because it's very succinct and very accessible and slightly more detailed than what I've been able to go into here. So thank you very much.
Questions?
Good catch.
Thank you very much for this very nice talk. So my question is about the classical cost of computing these new decompositions, because I would imagine that possibly, I don't know, maybe you can comment whether they go up corresponding to the earlier ones and whether like the classical savings outperforms like the quantum.
No, so, oh gosh, can I go all the way back? So if you recall the four-step kind of process for approximation, the classical steps are kind of this point enumeration step and this solving the norm equation step. But we can do those both in polytime in the dimension of the field that relates to your gate set. So using our method, which really only affects that first step, has no effect on the next two steps.
Okay.
Yeah.
Sort of a slightly related question, but assuming it's polynomial, do you, like, sort of how fast is it in practice? Because I guess if you want to do these kind of synthesis, you have to sort of, maybe you want to do it interactively. How much, does it take significantly more work to do your algorithm over the previous ones? Just like in a sort of actual time-based factor, like how long does it take to run on a, laptop?
So no, because, so I mean, for the like standard diagonal case, it's just the same. And then for the other cases, they were kind of using that as a black box anyway. So in our method, because we can approximate directly, you're not increasing the cost, basically.
All right, thanks. I have another question, if
Oh,
I
yeah,
may.
go for it.
So you showed sort of plots for average gates, and the variances are not very big, so that's actually a pretty good representation, but they're not non-zero, right? So do you have any idea what the worst angles theta are, and are they different for different algorithms?
I don't have an idea of that, unfortunately. I would have to look at the paper. But there are instances where you get a much cheaper approximation. So if you're using Fourier angles, for example, often the identity is a good enough approximation. And that's where we see this kind of area gets pulled all the way down to zero, for example. Sorry, this isn't an exact answer to your question.
No, but it's a pretty good one. I like it.
Yeah. I don't know exactly what angles are giving the worst cost. No, sorry.
Thank you very much for the talk. I'm wondering, at the fourth step, you talk about the exact synthesis. It's actually along the same line as the question that he asked. In terms of the complexity of running this algorithm, does it come from finding the integer points from the enumeration, or it comes from exact synthesis at the fourth step?
That is a good question. Let me just get the process. I think most of it would... Okay, I'm not 100% sure, but I do think you're right that a large proportion of the complexity would end up being in that fourth step. But that's our black box, I guess. We've kind of employed that step using existing exact synthesis algorithms there.
So, for example, Giles-Salinger algorithm?
Yeah.
Okay. Yeah.
Sorry. This isn't a great depiction of what we do, but we do actually, in our paper, give improvements to exact synthesis over Clifford plus T and Clifford plus root T. So it's not general, but we make improvements to those two cases.
Thank you. And I'm curious, this is a very naive question. So you said you can extend the algebraic structure from Clifford plus T to quaternion algebra. I wonder, have you thought about it doing this reverse way, for example, from Clifford plus T to restricted Clifford plus T? For example, in 2020, yeah?
I'm saying, ooh, that's a great idea.
Yeah. I'm curious because sometimes maybe we only need a proximate universal key set that is not as powerful as Clifford plus T to carry out quantum task. So I'm just curious whether you have thought about it in this direction.
We have not, but that sounds great, and I would love to talk to you about that after, yeah.
Thank you.
So going back to early on you had a chart of constants, leading constants, and there's one that I'd like to ask about, which is the strict lower bound that you get from the volume argument for the constant that you know that you can't beat. What is that what is that compared to what you're getting?
So for the diagonal case, it is this 3, but it's the volume argument doesn't assume the ability for like fallback, which uses an ancilla, or for mixing. So it looks like we're beating that strict lower bound, but it's proved for kind of a different case. And then if you're thinking about so single qubit unitary approximation, the average case lower bound would be 4, and the worst case lower bound is 6. So if you recall, we reduced our cost to 7 log 1 over epsilon. So we get close to that lower bound, but we're not on it.
7 rather than 6.
Yeah.
Okay. Okay.
So
Very
it's
interesting.
all right.
Thank you.
Great. So let's thank Romy again.